So remember, as we talked about last time, acids are substances that can produce H plus ions in solution. And again, what we're talking about when we talk about that is the ability to produce really free floating H plus ions, so not attached to anything, just the ability to sort of release that into the solution and have it floating around freely. Also, remember that in acid-base chemistry, when we're dealing with H plus, that is the same as H3O plus, which is the hydronium ion. So they are used sort of interchangeable in both formulas, also equations as well. And that's different than a base that has the ability to produce hydroxide, OH minus. And same idea, if it's something that's a base, it'll be able to produce free floating OH minus in solution. Once again, not really attached to anything, just kind of floating around. And that's what we'll talk about. And as we did talk about, the relationship to how much H plus is in the solution to OH minus that's in the solution will determine whether or not the solution will be acidic, basic, or neutral. We talked about the Bronsted-Lowry definition of an acid and base. And the Bronsted-Lowry definition, an acid is a proton donor. And remember, a proton is another sort of word we use for H plus. So something that will give it away. And a base is a proton acceptor. And sort of the consequence of the Bronsted-Lowry definition is you will create partners. So you'll have an acid plus a base, and it will make what is referred to as a conjugate acid or a conjugate base. And these guys are related to each other. So the acid on one side is related to the conjugate base on the other. And the base on one side is related to the conjugate acid. And really the only difference here is the definition of an acid, which is it will send over one H plus. So there is only one H plus difference in order for something to be a pair. If it's anything more than one H plus, then they are not considered a Bronsted-Lowry pair. We saw maybe something like we could look at HCl plus some water going to form H3O plus and some chloride. And once again, this is our acid. The water in this case is acting as a base. Again, the acid's going to send the H plus over. When it does so, it will lose the H plus and become Cl minus, and that is the conjugate base on this side. The water, which will accept the H plus, will make H3O plus, which is the conjugate acid. So once again, the only difference between those two is one H plus. The HCl has to the Cl minus has one less H plus as it lost it, and the base to the conjugate acid has one more H plus because it gained it. The other important thing that we talked about as well is the idea that it's not just a hydrogen, but it does have a plus charge. So your conjugate acids or conjugate bases will have some adjustment. Thank you. Will have some adjustment in terms of their charge when they either gain or lose that H plus. So when you gain an H plus, you become one more positive. Obviously, when you lose an H plus, which is a proton, you have more electrons than protons, you become one more negative. So the sign changes as you go through that. As well. But you always find on the left-hand side of the arrow just your regular sort of acid and bases. On the right-hand side of the arrow is where you find all your conjugate kind of partners there, your conjugate acid or conjugate base. Remember as well that we talked about you can have something that's a diprotic acid or a triprotic acid, which means that it can lose more than one hydrogen, but they do come off one at a time. So they just don't all just kind of fall off at once. So it is a stepwise process as to how they come off. So I think we looked at like sulfuric acid, which is diprotic. It will actually lose one H plus first and then become HSO4 minus. And then that HSO4 minus will lose a second H plus and become sulfate. And in terms of acid and conjugate base pairs, that is why, as we talked about this guy here and this guy, they are pairs. And that's why this one right here and sulfate are actually pairs. Also why if you go from H2SO4 to SO4 2 minus, they are not pairs, as the difference there is again more than one H plus. So it is not considered a conjugate base pair, even though they are sort of related to each other. The difference there is more than one H plus. So it has to be only one H plus difference. We then got into idea, obviously, of amphoteric substances like water, and water can react with itself, um, and it will form an equilibrium and set up an equilibrium. We could have an equilibrium constant for really the dissociation of water or water reacting with itself. If you want to put both waters in there, you could as well. And again, in one case, one will donate, one will accept. We'll make H3O plus and OH minus, right? And since this is an equilibrium, you can write an equilibrium expression, which is the capital K, that's known as KW. Concentration of H plus times concentration of OH minus equals 1 times 10 to the minus 14. That is essentially a constant. It does change with temperature, but for our purposes, you'll never see it probably other than that number, 1 times 10 to the minus 14. And what that allows you to do is if you know the H plus concentration or the OH minus concentration, you can figure out the other concentration by just simply taking 1 times 10 to the minus 14 and divided by the concentration of the other. A reminder again that these brackets mean concentration, and usually that is molarity we're talking about here in terms of units. Also, OH minus here would be 1 times 10 to the minus 14 divided by the H plus concentration. You could also write it for this relationship here as well. Again, you could substitute in the H3O plus if you like, and that's probably how a lot of books will do it. And again, it is the same thing. So if you want to use H3O plus, it's perfectly fine. If you want to use H plus, it's perfectly fine. They're both basically the same. This is basically the acid part of the solution. This is basically the base part of the solution. So once you calculate those, you can compare them. And if the H plus concentration is larger than the OH minus, then you have an acidic solution. If the H plus concentration is lower than the OH minus, or the OH minus is bigger, you will have a basic solution. And if they equal each other, they will equal 1 times 10 to the minus 18, 1 times 10 to the minus 7, which will be neutral in that case. And the relationship between H plus and OH minus is basically an opposite relationship. So as one goes up, the other goes down. So kind of vice versa. H plus goes down, the OH minus will go up. So as one goes up, the other goes down, and that is how the relationship sort of works. And that's why, again, a solution becomes more acidic or basic, depending on what's happening. It becomes more acidic, you have a lot more H plus than you do OH minus, and vice versa. Any questions on any of that there? Also, obviously, as we talked about, you definitely want to make sure you use your exponent button when you're punching these things in, otherwise you will be in some trouble in this chapter. All right, so I think we did the first one here. So why don't you do the others? And for these other three, we're looking for either the H plus or the OH minus, depending on which one's given to you. And is it acidic, basic, or neutral? So take a few moments there for each of these here and calculate up what you come up with. So obviously for the first one here, we're looking for the OH minus. And we're looking for the H plus concentrations for the other two. Okay, so let's take a look. So the good news on this one again is it's pretty much the same calculation, regardless of which one you're given. So since our KW equals the H plus concentration times the OH minus concentration, that equals 1 times 10 to the minus 14. It really doesn't matter which one you have. You're basically going to take 1 times 10 to the minus 14 divided by the other concentration. So in this case, we'll look for the OH minus, 1 times 10 to the minus 14 divided by the H plus, and popping in our number there. Again, making sure to use your exponent button 1 to the minus 14 divided by 2.6 to the minus 8 should yield you something like 3.8 times 10 to the minus 7 molar as our hydroxide concentration. Or something, any question on the calculation there? Once again, the property punch it in, one exponent button, negative button, 14, divide 2.6. Once again, exponent button, negative button, and 8. And that should get you there. All right, now that we do have our concentrations, we want to compare these two concentrations, see which one maybe is larger. So when we look at both of these here, you hopefully should recognize that it actually is the OH minus that is larger. A reminder as well, sometimes people screw this up by just looking at the numbers here. But the negative, once again, is important. So when you have a negative exponent, again, the smaller negative exponent is actually the larger number. And that's because in this case, we're going 7 places this way and putting zeros. But here we're going 8 places that way and putting zeros, which makes it a smaller number. So in this case, the hydroxide is bigger, which means this should be basic in this case. Any questions on that one there? All right, so taking a look at the next one, again, pretty much same calculation. We're going to go our H plus, 1 times 10 to the minus 14 divided by our OH minus 6.2 times 10 to the minus 9. Again, making sure to punch it in correctly with our exponent button is going to get us here. Not that. Get rid of that. Hit that. Nope. Let's try one more time here. There we go. It looks like it's going to get us 1.6 times 10 to the minus 6 molar. We do need molarity there as it is a concentration, so we do need units. And again, we want to compare these two. And in this particular case, it is the H plus concentration that is larger in comparison. You can pretty much just compare the times 10 parts if you want. And because of that, it would be acidic as the acid part is greater than the base part in this solution. Any questions on that one? All right, next one, same deal. We're going to go H plus equals 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. Gets us 1.2 times 10 to the minus 12 molar in this case. Once again, comparing our two concentrations, we do see that it is definitely the hydroxide that is larger as to the minus 3 versus minus 12. Again, we're only going 3 places to the left and putting zeros. Here we're going 12 places and adding zeros. And that makes it a much, much smaller number in that case. And that would mean that this is going to be basic. Any questions on those calculations there? Again, for most people, the punching it in, the exponent, and the comparison part sometimes is troublesome. Again, remember negative, smaller number, larger, in terms of the exponent. All right, take a look at a couple more here. What is the OH minus concentration? And is it acidic, basic, or neutral? So take a moment there and calculate. Okay, so again, OH minus here using our KW value, which is pretty much a constant for us, 1 times 10 to the minus 14 divided by what was given 2.8 times 10 to the minus 5. That's going to get us here 1 to the minus 14 divided by 2.8 to the minus 5. Looks like 3.6 times 10 to the minus 10 molar. Once again, we're going to compare the H plus concentration to the OH minus concentration. So OH minus is 10 to the minus 10. This is 10 to the minus 5. That should mean that the H plus is larger than the OH minus. And that would also mean that basically the acid part is bigger. So this solution should be acidic in this case. Any questions on KW here? So again, it is a thing that you always have. Not very much mentioned a lot of times in problems. I'm actually going to skip that one, I think. All right, the next thing we're going to talk about actually is the pH scale. And the pH scale is a measure of acidity, and that's not negative. This is from PowerPoint. So the pH scale runs from 0 to 7 to 14. Less than 7 is acidic. Above 7 is basic. And really dead on 7 there is neutral. 7 is sort of the center point of the pH scale. And as you go from 7 towards 0, you're becoming more acidic. And as you go from 7 towards 14, you're becoming more basic in that case. And to calculate the pH, it pretty much is the formula we see on the bottom there. The pH is equal to negative log of the H plus concentration. It tells you actually in the name kind of what you need to calculate it. You need the H plus concentration. This is another one of those formulas that if you want, and you most commonly will see it with the H3O plus. So again, they are basically the exact same deal. It's the H plus or H3O plus, whichever one you want to kind of put in there. So same thing. Now, this will give you a value when you calculate it. And let's talk a little bit about your calculator and this formula. So depending on the type of calculator you have, this formula and probably the rest of them from this chapter, you may have to kind of input it into your calculator kind of one way or the other. So if you have a display calculator, you're basically just going to put the formula in exactly the way it's written. You're going to go negative, your negative button. You're going to hit your log button. And then you're going to put your number in, obviously using your exponent button. If you have a non-display calculator, this formula, and pretty much most of them that we're going to see in this chapter, you need to kind of go backwards. You need to actually start with the number using probably your exponent button. You then need to hit the log button, and then you need to hit the negative button. So kind of display calculator, just the way it's written, kind of non-display. You got to kind of go in the backwards way with all these formulas. How do you know if you have a display calculator or a non-display calculator? Pretty much hit the log button. And if you hit the log button on your calculator and it says log on the screen, congratulations, you have a display calculator. If you hit the log button and it says error, or you get an error message, you have a non-display calculator. So that's a quick way to know which one you should do. By just hitting the log button. So we use the pH to help us determine if a solution is acidic, basic, or neutral. And again, this is another way we could do that. Now I'll talk a little bit about significant figures and pH. So the rule for significant figures and pH is this. The number of decimal places you should have in like your pH answer should be equal to the number of significant figures there is in the concentration that you're using. So whatever number of significant figures there is in the concentration is not how many significant figures you should have in your answer, but it is how many decimal places your pH or pH-like value should have. And when you're going backwards, if you happen to be going from pH back to concentration, it works the same way. It is decimal places to significant figures. So just to make sure, let's try a couple here. What is the pH of this solution that has an H plus concentration of 1 times 10 to the minus 5? And write it down with the proper number of significant figures. So let's take a look. So obviously here we want to calculate the pH. So that is negative log of the H plus concentration. We're obviously given the H plus concentration, which is what we need to calculate it. Again, you'll put it into your calculator one of two ways. If you have a display calculator, you're going to go your negative button. You're going to go your log button. And you're going to go your 1 exponent button, negative button, and 5, and hit equals. If you have a non-display, you're going to start with your 1, your exponent button, your negative button, your 5, then you're going to hit your log button, and then you're going to hit your negative button one more time. No matter which way you do that, staring at you on the screen should hopefully be a 5, I hope, on your calculator. And that is the pH of the solution. So now that we've hopefully calculated it correctly, we do need to sort of give the answer correctly as well. So should the answer be 5? Should it be 5.0? Should it be 5.00? So again, the rule is the number of decimal places we should have in our pH answer should equal the number of significant figures in our concentration. So this is our concentration. It is written in scientific notation, which means it has 2 significant figures. And because it has 2 significant figures, the answer should have not 2 significant figures, but should have 2 decimal places. So our correct answer here should be 5.00. It has 2 decimal places because the concentration had 2 significant figures. So we are going from significant figures to decimal places, not sig figs to sig figs in this case. First off, any questions on that calculation there? Now, this would also mean that the pH here is less than 7, which means this solution should be acidic, as again, we have a pH value that is less than 7. Any questions on that there? Okay. All right, so why don't you take a few moments here, calculate the pH for each of the following, and determine is it acidic, basic, or neutral for each of them. Make sure you know how to punch it into your calculator. Let's take a look. So on the first one here, we do have the H plus concentration. So because of that, we could go right into our pH equation minus log of the H plus. Again, it tells you what you need. So putting that in, negative log of 2.1 times 10 to the minus 5. Again, making sure you punch it in whichever way you need to based on your calculator. So you also use your exponent button. Gonna give me a 4.68 pH. pH is just a number. There are no units associated with it. Here, our original number had 2 significant figures. So once again, we end up with 2 decimal places. Again, not significant figures on the pH, so decimal places. So those 2 sig figs gives us 2 decimal places on the pH. That is definitely a pH that is less than 7. So that is going to be acidic as well. Any questions on that calculation there? All right, take a look at the second one. We are actually looking for the pH as well. So the pH is equal to minus log of the H plus. Again, it tells us what we need, which is the H plus. Unfortunately here, this is not the H plus concentration. That is the OH minus concentration. That means we can use our KW like we did previously, that the H plus would equal 1 times 10 to the minus 14 divided by our OH minus 5.9 to the minus 8. And we will end up with the H plus concentration, which is really what we need to go into our pH equation. And that's 1 point, I'll just round it, 7 times 10 to the minus 7 molar. Now that I do have the H plus, I could go into this, and that would give me a pH that is equal to negative log 1.7 times 10 to the minus 7. I'm going to use the whole number on my calculator, not the rounded version here. And that's going to give me a pH of 6.77 in this case. And that is slightly less than 7, which means it is slightly acidic. We are going to go with neutral being 7 on the nose because technically speaking, if you're neutral, the H plus concentration equals the OH minus concentration, which equals 1 times 10 to the minus 7, which if you calculate the pH would be a pH of exactly 7. So we are going to go 7 as being neutral or super, super close to 7, like 6.999 or something like that. If it's not 7, it's either going to be slightly basic if it's above or slightly acidic in this case. Now, if you weren't very careful in this particular case and you just decided, hey, I know a formula here, we're just going to put this into here minus the log of the number that was given to us. You ended up with this number minus the log of 5.9 to the minus 8, and you ended up with something like 7.23. Now, obviously, you did not calculate the pH as we just calculated the pH, and that is because you did not use the H plus concentration here, but you did use the OH minus concentration. So instead of calculating the pH, you actually calculated what is known as the POH, which obviously needs the OH minus concentration. And that's not necessarily a bad thing because, as we'll see in a couple of slides down the road here, if you take the pH plus the POH, it will actually equal 14. And that means that if you took the pH, would be 14 minus 7.23. That gets you to the pH here. So it does give you a variety of ways you can maybe solve for it, but there is a difference between the pH and the POH. So 7.23 would be the incorrect answer for this problem, as that is not the pH of this solution. Any questions on that there? All right. Now the pH scale is based on the log of 10. And for every power of 10 change in the H plus concentration, you also see a pH change. So a pH of 3 has a H plus concentration of 1 times 10 to the minus 3. pH of 4, 1 times 10 to the minus 4, 1 times 10 to the minus 5 is a pH of 5. Pretty much if you need the pH of anything that's 1 times 10 to the minus whatever, it's equal to the exponent. You don't really need a calculator to do that. The pH scale in H plus, as the H plus concentration increases, the pH decreases. It becomes more acidic. And that is because as the H plus concentration goes up, the OH minus concentration will go down, and you have a lot more H plus in the solution, making it more acidic, so the pH will go down. Vice versa, as the H plus concentration goes down, the OH minus concentration goes up, and that's going to make it more basic, and you will see the pH go up as well. So again, if you have more H plus, lower pH, more OH minus, more of a higher pH, you should sort of see in that case. Any questions on that there? Talk about a couple different ways that you can measure the pH. A very common way is actually to use a pH meter. pH meter is an electrode here, and it actually measures the H plus concentration, the free H pluses that are floating around in that solution. What you really do is you have 3 standards usually that you use that has a pH of 4, a pH of 7, a pH of 10. And basically it reads voltages and it makes a calibration curve, and basically when you put it into your solution, it goes, oh cool, it has this voltage, that means it's a pH of whatever it may be associated with it. Nice thing about a pH meter is it's got basically a digital display and will just tell you straight up what it is. Another way that you can check the pH is to dip something like some pH paper in there. And if you ever checked like a pool or anything like that, those kind of pool strips are very similar to that. You dip it in there and then you try to match up all the colors to a color key. And it's not perfectly accurate because you got to try to find all the color matches. And you can find, okay, well, maybe it's a pH of 1, 2, 3 or so. So these are 2 very common ways we can measure pH. We also use litmus paper. It is not to measure the pH, but it will tell us is it acidic or basic. So sometimes we'll use litmus paper to help us determine if some solution is acidic or basic. Once again, it doesn't tell you the exact pH or anything like that. It just basically tells you whether or not the solution is acidic or basic. Typically, if you have red litmus paper and it goes to blue, that means it's basic, or basic is blue. And if you have blue litmus paper and it turns to red or stays red, it's acidic. So typically litmus paper is red, stays red, turns red, it's an acidic solution. If it turns blue, the litmus paper, or stays blue, it's a basic solution. It's typically what we use litmus. Once again, it doesn't tell you the pH, but does tell you uh, if it's acidic or basic. Here's a pH scale and some of the stuff we find on it. Again, we have sodium hydroxide, which is a strong base, way up there in the basic range. Strong acids, hydrochloric acid, obviously down there in the uh, acidic range. We have a lot of vinegar, lemon, stomach acid, acidic. A lot of cleaners are basic. Pure water is 7. Most water, though, is not probably pure water, especially if you take water that's been sitting out a while. People are sometimes surprised it's probably in this range in terms of the pH, and that is because it picks up some CO2 from the air, plus some water makes some carbonic acid, and that increases the H plus concentration in that solution and makes it a little bit more acidic. And sometimes if you need your water to be really neutral, you'll boil your water. When you boil your water, it makes the CO2 less soluble in the liquid part, goes out, and raises the pH back up to 7-ish in that case. Years ago in buildings that are really old, when you did titration experiments like you did in class, you would usually boil your water when you're making your solutions to get rid of that CO2 to kind of get into a neutral space. Now they're sealed much better than they used to be, the buildings, so they don't worry too much about it. All right, so we kind of touched upon this a second ago, but there is another scale that is similar to pH, but it does measure the OH minus concentration, and that is the POH. It is punched into your calculator the exact same way you would punch in the pH, depending if you have a display or non-display. Once again, the name tells you what you need. So POH, you definitely need the OH minus concentration. Just like we saw our pH, you need the H plus concentration. So again, the name kind of tells you that. Um, and then that nice relationship there that the pH plus the POH does equal 14. Now, it's really important to understand as well that the POH scale is opposite of the pH scale. So the pH scale, as we just talked about, is 0 to 7 to 14. And once again here, less than 7 is acidic, above 7 is basic, and 7 obviously is neutral. Now, if you look at the POH scale, it also runs from 0 to 7 to 14, but it is different. Less than 7 is basic, above 7 is acidic, and 7, once again, is neutral in this case. So they are opposite of each other. So if you have a low pH, you should have a high POH, and vice versa. If you have a high pH, you should have a low POH. So they do run opposite of each other. I would highly recommend that you should probably always look at the pH scale when you're trying to determine if it's acidic, basic, or neutral. That is the scale everybody has in their head. Very few people have this scale in their head. And that will always give you the right answer. Which, by the way, when you are asked that question, is the solution acidic, basic, or neutral? There is only one answer to that. It should be acidic, or it should be basic, or it should be neutral. It cannot be acidic and basic at the same time. Otherwise, I think you have a neutral solution at that point, but it cannot be. Why do people sometimes say that? Is because of this. I've never had anybody really do all three of them, but I have had many people for the same solution call it acidic and basic at the same time, and that's because they calculate the pH and go, cool, it's less than 7, it's acidic, and then they calculate the POH and go, cool, it's above 7, so it's basic. So again, always look at the pH and only give one answer for that question of is it acidic, basic, or neutral. If we add in here our other sort of information, our Kw that we saw earlier, which was our H plus and our OH minus equals 1 times 10 to the minus 14. It does give you a variety of ways you can solve these problems depending on which way you want to go. Every way should give you the same answer if you do it correctly, so it doesn't really matter which choice you wanted. Like on the previous example, you could have done the POH and subtracted 14 and got the pH, or you could use KW like we did and also get the pH and get the same answer, so it doesn't really matter which way you go. One more couple of things to add to our list of sort of formulas here, and that is if you have the pH given to you, you can directly from it get the H plus concentration. So you could directly get the H plus concentration by taking the inverse log of the negative pH. So if you have the pH given to you, you can just put it into this formula and get the H plus concentration from it, or the H3O plus concentration from it. On most people's calculators, when you hit inverse log, it pops up at 10 and a caret on most people's calculators, and you want to make sure it's negative pH that you put in there. So that is usually what it looks like. By the way, on most people's calculators, to get to that upper left corner, you have a shift button or a second button, and then you have your log button, which typically has a 10 to the x above it, which is what most people sometimes use for scientific notation incorrectly. And this is definitely a place where you would not want to do that. So shift and log should usually get you to the inverse log. And a reminder that if you have a display calculator, you need to punch it in exactly the way it's written. So once again, if you have a display, you're going to go your shift or second button, whichever one you have in top left. You're going to go your log. You're going to go your negative, and then you're going to put your pH in. Or if you have a non-display, you actually need to start with the pH. You then need to hit your negative button. You then need to hit your shift or second button, and then you need to hit the log button. So once again, you got to work backwards if you have a non-display calculator. So depending on which one you have. Any questions on that there? Now, we could also do this, as it may not be surprising to you, we could also do this with POH. And if you have the POH, you could directly get the OH minus from it. Good news is it is the exact same calculation. So it is the inverse log of the negative POH. Once again, on most people's calculators, it will kind of show up something looking like this. You hit the exact same buttons here, except you put the POH in rather than the pH. So you punch it in the exact same way for both of those. So this adds again another options in terms of which path you may choose. It is probably based on what is given to you as to which way you should go. But pretty much there are multiple ways you can get to the same answer here, depending on the information you have. Any questions on any of those there? Yeah. And by the way, if we are doing this calculation, this is when we would be going from decimal places in our pH or POH number to significant figures in our concentration. So we're going backwards here. So we would go from, in this case, decimal places to concentration, which would be sig figs. Yeah. And the same thing here, we would be going from decimal places to sig figs, going backwards. All right, any questions on that there? All right, let's try some here, maybe. All right, so for each of these, let's just make sure our calculators work. Let's calculate for the first one here. Let's do the OH minus concentration. Let's do the pH and the POH. And is it acidic, basic, or neutral? And for the second one, let's do the H plus concentration, the pH, the POH, and is it acidic, basic, or neutral? Okay, so let's take a look. So since we're pretty much looking to calculate everything. Like I said, with everything that we just talked about, we do have some options as to where we want to start. So it's up to you. I'm going to start here. Since we do have the H plus, we could do one of two things. We can, since we're looking for everything, we could get the pH directly from that. We could also use Kw and get the OH minus concentration. So it's really your choice, whichever way you want to start. I'm going to start with the pH. So the pH here is going to be negative log of my H plus, which is 3.6 times 10 to the minus 9. That is going to give me a pH value here minus log of 3.6 to the minus 9. Looks like a 8.44. Now, at this point, I have the pH as well. I could get the pOH very easily from it by using that relationship that the pH plus the pOH equals 14. That means that our pOH here would be 14 minus 8.44, and that's going to give me 5.56 as my pOH in this case. Once again, at this point, I actually still have a multiple of options to get the OH minus concentration. Now that I have the pOH, I could get it from that. I could also still use Kw and get the OH minus concentration. But I'm going to do it the kind of newish way that we just talked about. So I'm going to use that the pOH will get me the OH minus concentration by taking the inverse log of the minus pOH. So again, on your calculator, it should look something like this when you punch it in. And again, if you have a display calculator, you would punch in your second or shift button, your log button, your negative button, and 5.56 and hit equals. If you have a non-display calculator, you would hit 5.56, then your negative button, then your second or shift button, and then your log button. So again, either way you do that, hopefully you will end up with, if I hit the right button on my calculator, there you go. You'll end up with something like 2.8 times 10 to the minus 6, and this does need molarity as it is a concentration. Now, again, a reminder that if you wanted to use Kw up front, you could have done that as well. So you could have just done our 1 times 10 to the minus 14 divided by our H plus concentration, 3.6 times 10 to the minus 9 will equal your 2.8 times 10 to the minus 6 molar as well. So again, you could still use Kw if you wanted to, like we did previously. First off, any questions on any of those calculations there? Now, we do want to know, is it acidic, basic, or neutral? Remember, when you have a lot of these numbers, so you do not make a mistake, always look at the pH. Yeah, so here the pH is 8.44. That definitely is above 7, which means that this solution is basic in this case. Any questions on that? Again, should only be one answer for that question. All right, let's take a look at the other one. Again, here on the other one, we do have two options up front since we're looking for everything. We could definitely use this and Kw to get to the H plus. We also could get the pOH directly from that number. So that's what I'm going to do. I'm going to do the pOH first. So the pOH is equal to negative log of the OH minus. That's going to be negative log of 9.2 times 10 to the minus 2. Once again, on your display calculator, negative log 9.2 exponent button, negative button, and 2, and hit equals. Non-display, 9.2 exponent button, negative, and 2, and log and negative. All right, so if you do any of those guys there, you should end up with 9.2 to the minus 2. Looks like 1.04 is going to be our pOH. Now that I have my pOH, I again could use that relationship that the pH plus the pOH equals 14. That's going to give me, in this case, the pH is equal to 14 minus 1.04, which is our pOH. So that's going to get me a 1296 here on my pH in this case. We are looking for the H plus concentration. So once again, we can use the pH to do that. And the H plus concentration will equal the inverse log of the negative pH. Once again, on your calculator, if you punch it in just like over here, you should end up with a 10 and a caret, negative 12.96. And that will get us here. Punch in the right number. It'll get us, it looks like a 1.1 times 10 to the minus 13 molar. Again, you could also use kW just like we did over here. And you could have done 1 times 10 to the minus 14 divided by our 9.2 times 10 to the minus 2. And that should also get you there as well. Once again, here we do want to look at our pH to help us determine. Our pH is actually 12.96. That once again means it is above 7, which means it is basic in this case as well. First off, any questions on that there? Couple last little notes here on these calculations. We were going from here, our pH, which was our, well, actually, we did our pOH here. We went from 2 significant figures to 2 decimal places. When we went backwards, we had 2 decimal places, gave us 2 significant figures as we go backwards. So again, works the same way, same here. We had 2 significant figures, gave us 2 decimal places. Going backwards here, 2 decimal places give us 2 significant figures. So again, the rule works both ways. It's kind of forward and backwards as well. Any questions on that there? All right. Well,